So used to when we first got into these computers that came out, we had to enter everything by text, and we used something called command prompt. And it's still available. It's in the set. And if you ever get into, so we had a big screen that came up with nothing but this. Had a little command line, and it's got this little flashing thing on there that we call a cursor for obvious reasons. Then what you're doing is and if you ever get into networking, this is a very important because your TCP/IP protocol suite, it uses this a lot. And one thing we'll use is what we call config sys. Oh, I'm sorry, IP config. And this is going to tell you all this information about your network adapters in your computer. Oops. IP config. As soon as I spelled it right. Config, Rich. So this is all the guys that need IP addresses in my computer. So this is my IP address right here for this local network card. So it's 169.254.163.226. Now what this is, it's a 32-bit binary number, but they understand that the average person would not be able to enter a 32-bit binary number. So what they did is they split it into groups of 8 that some people call an octet. And then they have 8 bits for each octet, which means we could have from 0 to 255 combinations. You'll never see anything above 255 because it's a binary number, right? You understand? This is assigned automatically. If we set it up as dynamic IPs, then this is assigned automatically. If we set it up for static IPs, so when I come up here, I'm going to go to control panel, and then I'm going to go to network, and then I'm going to go to my adapter settings, and this is my local network, and then properties. Oops. Properties, Rich. And of course, here's our TCP/IP protocol suite. We were using one. First of all, it was the version 4, which is IPv4. This is the 32-bit number. They have added, so we had 232 2 to the 32nd IP addresses available. That's a big number. And they thought they would never run out. So they made some of them for private networks. They made some of them for the internet. They made some of them for the government. And then they said, well, we'll still never run out. But how many IP addresses do you think you use in your house? I probably use, 22 maybe, yeah. So that's what they never envisioned. They never envisioned that if you connect to the internet through anything, you got to have an IP address. So your cell phone, every cell phone in your house has an IP address. If you've got computers connected wirelessly, if you got a tablet, if you got all these different, if you've got a doorbell on your house that you can access through the internet, it's got a what? It's got an IP address. So they came out with IPv6, which is going over to the internet. This is a 148-bit binary number, so that's 2 to the 148. So guys, that should get us through our lifetime. Basically, but if you're on a private network, if you're not on the internet, then we're still using IPv4, and these are private networks. So how many devices can have the same IP address on the internet? One. How many devices can have the same IP addresses on private networks? You just can't have the same one on our private network. So 175, there's several that would be there. So I'm going to click on IPv4, and this is the property. So right now I have mine set up for dynamic IP. So obtain IP address automatically. It comes up and it fills in your IP address, your subnet mask, and your default gateway. A gateway is a computer or an application that converts protocols. So inside our network, we're we're using a technology of transferring information we call baseband. Baseband is one computer at a time. When we go out on the internet, it uses broadband. So that means we got to have a gateway that we go through that transfers from baseband over to broadband. So everybody and normally when you buy your router, all this is built into it. It might be built into your modem. If I wanted to manually assign my IPs, and why we manually assign IPs is that if I turn my computer off, I think our DHCP server has like a week lease. So once it's assigned me an IP address, it lets me keep that unless I turn my computer off for a week. If I turn my computer off for a week, then I get a new IP address. We can't have file servers and domain servers moving around. So all those servers have use static IPs. So we've got our own subnet over in our lab. Normally we use dynamic IPs. And why? Because you don't have to do it. You got to have a DHCP server that does that for you, right? That makes sense. Okay. So that means right now this guy here does not have a IP address. And if it don't have an IP address, then and it uses dynamic IPs. So the first thing it's going to do when I turn it on, it's going to broadcast looking for a DHCP server saying, hey, I need a what? I need an IP address for your. And since I don't have a DHCP server because I have this thing connected directly to my computer, then I've got to make that service available. Everybody okay so far? This makes sense? So that means I hooked my computer up. This is the first time I did it. This guy don't have a battery in it, so every time, so don't unplug your PLC down there because we'd have to do this because if I turn this guy here off or unplug it, then it's going to lose the IP address because of the battery. So most of these things have a little slot you keep a battery in. And that's one of the things you might lose if you're running Ethernet IP. If you lose that battery, you might lose your what? Your IP address. Okay, so I'm going to come up here. I'm going to go to all programs, and then this is one of the things that's in your suite. So RS Logic software, and here it is. This is a DHCP server. That means I can now if I had this on a true full-blown network, it would get one, right? You understand that? Does that make sense? But we have to simulate it here, so I'm going to run my DHCP server. And first of all, it's asking me, okay, what do you have this thing connected to? I have it connected to my gigabyte network connection. That's my actual network circuitry inside my laptop. And what it's doing is looking for what we call MAC addresses. We talked about that. What's a MAC address? Yeah, it is the physical address that's built into these devices. So this is the physical. So your phone has a MAC address. That MAC address cannot be changed by the end user. So there it is right there. So I've been using it enough. I can show you where to get it. Usually, if you look on them, it'll be written somewhere on the front or the side. I'll show y'all this one. This one you have to go through a menu. I'm going to double click on this. This shows me the IP that's assigned to my my network card, 169.254.163. Then it shows me the actual MAC address of the PLC. This is built in, so everybody, so that's a 48 number. We still haven't run out of those yet. The way it's set up is the first 24 bits identifies the most significant 24 bits identifies a manufacturer. So, and then the last 24 bits identifies a card. So that means you could have 2 to the 24th addresses for each manufacturer code. And then if the manufacturer runs out of that many, they ask for another what? Another manufacturer code. So we're well within this. 2 to the 48th. That's how many of these things we could have. On this, guys, I have to assign the first 4 numbers the same. So 169 and 169, Rich. You'll never find it. 254, 163, and then the other one we'll use that. I'll use 100. And then I say okay. And then when it assigns it, it'll come up here and actually say, I've assigned it to it. So for okay, there we go. So now we got an IP address. Next, what I would have to do is I would have to go into RS links and make sure I have the Ethernet driver loaded. As soon as I get my brain in order. So they provide this with you. So this is RS links. There it is. And this is what I showed y'all. This was up. Then we would have come in and make sure we have the right driver loaded. So where do we do that at? Y'all remember? Communication, right? Configure driver. So we have the Ethernet IP driver. If I didn't have it, I would have to do what? Add it. Okay. So we've got it running. I'm going to come up here and click on this guy to see if it can find it. So here's my Ethernet, and there's my PLC right there. So already I know I can communicate with it. You can also do this inside. So literally, this now with this, we could have multiple PLCs on the same Ethernet link, right? You understand that? Well, here we've only got one cable. But every one of them, we'd have to make sure every one of them got a different IP address. And then once we got that, then we could literally share information between the PLCs. Okay, so I'm ready to, I'm going to go up there and I'm going to go to comms. I'm going to go to system comms, and then there it is right there. So this is where you'd have to go to actually select a different PLC on your network. So literally, I could, if I've got switches and all this other kind of stuff that people have on these things, I could literally be in an office somewhere. I could hook up to Ethernet. I could, if I've added all these PLCs, I could select which PLC I want to go to. Of course, I've only got what? I've only got one. Okay, so we got the PLC selected. So, okay. So first thing we need to do right off the bat is make sure we have communication with the PLC, right? Okay. Now I'm ready to start a new program. What's the first thing I need to do? Where do I start a new program at? Go over here to this little white dot right here, right? Click that and then select. First thing it's going to ask me, and it surprised me since we had been in lab and everybody had done this, it surprised me that a lot of people miss this. Well, a few. So what do we need to know right now? Need to know the model of our PLC. Yeah. And y'all learned that. So what did somebody do? They just chose the first one. You'll hear Mr. Oath back here, right? And then when they tried to download it, it told them that it didn't know anything. I don't know what you got out there, guy. But we changed it over. I can show y'all where y'all can change it over if you do screw that up. So this information is going to be on the side of the PLC somewhere. The problem is that as soon as if I was to add more modules to these, what did I just cover up? I've covered up my information about my PLC, right? So y'all need to remember that and write that information down somewhere. So this is 1100B, and we've only got two down there. We've got the 1100. We got the 1100B series, and then we got the MicroLogic 1000 series, right? If you're on the little briefcase, you're on the MicroLogic 1000. If you're on the these guys, it's on the EduTrainer. These will be the MicroLogic 1100s. If you select the wrong CPU, you go out there and write your whole program. When it comes time to download it, it's not going to let you. It's going to say things don't match. Okay, so here we are. Now the next thing we would do is is we would come up here and we would configure the IO on the PLC. Now, true fixed PLC, you don't have that problem because a fixed PLC, you got what you bought, right? You understand that. But these guys right here, where you can slap these modules on the side, you're going to have to say, okay, what type of module do I have? And you need to buy the right module. So even if you did that, this would be a good place to look. And then you could go on Rockwell's website and then look up these part numbers over here on the left. And that's the way you could buy these modules. And how many modules can I put on this thing? I can put 4. Some PLC, this guy here, that's all we can put on this guy. Of course, we've got a lot of them. We hadn't put any modules on them yet. We do have some Siemens that I'll bring over here and show you all those when I give you a little hint of that works. So the first thing we do is select the CPU. The next thing we would do, if we have additional modules, if we have that rack over there, then what we need to do is we need to come over here and pull these little covers off of here. If I get it off. Off. And here's the actual part number down at the bottom. So you have to write all these down. Here goes down. It's 17 something down at the bottom. Yeah. And that's what you would have to do. You'd have to say, okay, in slot 1. So if I was dealing with that PLC, and I might hook one up, hook that thing back up before the end of the term and show you what we have to go through. So on those, you have to specify the slot. First of all, you have to specify the size rack you have. So we'd have to specify a 7-slot rack, and then we would have to say where we put these modules out. You don't have to put them in order. The only thing that's specified is the CPU card. The CPU module has to go in slot 0. But I could skip slot 1, 2, and stick something in 3. So I have to specify where these modules are at inside that rack. So I'll show you all that later on. Okay, now that we've selected the CPU, we've configured our I/O, then it's time to start programming, right? So what do we do now? Pull down our first what? Pull down our first rung. Notice our first rung will always be 0. The end automatically goes down. The end, you cannot put anything. So the last rung in these guys is the end rung. Somebody missed that one. Huh? Stop. Yeah, we okay? Okay. So then what would I do? I stop pulling down instructions, right? Very okay. I think this is, so we'll go ahead and make a parallel thing here. Now, what's nice about your book is your book is going to tell you your symbol names off of that. So another way we can assign symbols, guys, is you can come down here to the bottom, right here where it says what? Address symbols, and you can assign your symbols to start off with. So I could come up here and I could say add a new record, and we want to say input, colon, 0/0. Then I can hit tab. Oops, not tab. It says I require an address. Input, colon, 0/0. And then you can come over. Oh, I got it backwards. Oh, I'm sorry. Let's get this back. Okay. Add a record. Let's see. Take this record. Add a record. Oh, it moved up. I'm sorry. Then we can come up here. We can assign this already. And then what do? We just come up here to enter. Okay. Then what can you do? I could come over here and add another record. I could call this output 0/0, right? Tab over, call this red light. enter. I could come over here and add another record, call this output. Oops, output rich, output colon 0/1, a tab, and call this green light, and enter. And then what can I do now? Once I've got my symbol set up, then I can just come up here and start calling these things, right? What did I call this, by the way? I call it start, yeah. Now I can type up here. Now I can just type in. Yeah, as soon as I get there, guys. Start. Then I can come over here and type in this light. What did I call it? Light? No, I called it. Oh, I call it green. Now notice what happens. I come up here and hit that, and it pops up the symbols that start with what? G. And then I can just come down here and click on that, and it'll do that for me. Yeah, these are in parallel. So we have 2 lines in this. And the other one I call red light. And hit that. So what's nice about using symbols is that now you're not concerned with names. You're just concerned with, you're not concerned with these logical addresses. You're concerned with names, right? So we had somebody did that wrong. What were some of the things they did? Some of y'all typed in a symbol before you assigned it, and this is a symbol. We also can. By the way, here's another thing you can do. You can right click and you can change the instruction type. So right now we got it as an examine if closed. I could come up here and change it to examine if open if I want to, without deleting it and putting another symbol up there. I saw a bunch of y'all that did that. So you can change the instruction type, which is pretty neat. In fact, Siemens software has got a generic symbol that you just pull down there and you start typing the name, and it'll pop up all the different symbols, and you can. It's a lot faster than that. Another method that we have, instead of going through this and looking up all these things, you can bring up the palette of all the instructions that's available. And so this is all the instructions that's available. Right now we're not going to use all of them, and you could come in and pick them up this way too. So, and later on when you get into doing a lot of programming, this saves a lot of time to trying to figure out what group each instruction is. So what we have here is we have groups of instructions. We have user. User has the most often used instructions. So then we have bit. Well, notice a lot of the bit instructions are duplicated. So here's the examine if close, examine if open, output energize, output latch, output unlatch. Then we get into one shots, right? And then those are all bit instructions, and we're going to be looking at these timers. And then these are message instructions. So this is kind of confusing because you say input output. This is actually when we're sending messages and getting messages. So we could literally send a message up to this LCD screen right here, or to an HMI panel that would pop up. So we'll get into compare instructions next mini term, the math instructions, move instructions, shift instructions, sequencer instructions, and some program instructions. So that's what we'll get into if you're going to take the advanced PLC. Everybody got any questions? Is that okay? Okay. Any questions on that part of the test? And what I'm going to make sure I do is put that dictionary up there. Yes, and it's been, yeah, and hopefully y'all caught that. And if we were doing that, if we were doing this with this, and we'll put a contact here, and then I come over here and I do this, and I do this. notice it did it. But even if I come up here, I'm not going to sign. Oops, I'll get this right. Yeah, oh, I could still. Oh, I don't have this one. Input colon 0 0 slash 1. And then we can actually, I call that an input. That's going to give me a problem too. So I did that too. I put 0 slash 0. And output 0 slash 1. See, it does everything for you, but when I come up here and tell to check it for errors, then I can't clear the error. And down here it says inside file 2, inside rung 2, it says I've got an invalid output instruction position. And what's it trying to tell me? Yeah, I've got more than one output. It's in the wrong position, right? So that's why you need to always try to check it on compiling. It will give it to you when you try to upload it too. This is the big problem we have with that Logic Pro. You can get by with this on Logic Pro because it don't show you errors. So Logic Pro is a very impressive program, but you got to understand this guy had to do a lot of stuff that you couldn't do in a simulation. So you'd have to talk to the programmer. I mean, I didn't write the program, but that's a really good question, and it's very annoying too because, yeah, but it lets you get by with it, and it works. Yeah, it actually works in the program. So it's kind of confusing. So that was another problem, and so there was two of them that had that. We had one of them that I think we talked about in class, where we came by and did this. Oops, got to highlight the wrong weeks. Down at the bottom, Rich. Oh, that's supposed to be in there. Now this is, I'll come up here and check this. It's going to say, oh, I'm sorry. I didn't like that. I thought I selected that. So green. Undoubtedly it didn't. Okay, there we go. So it comes up here and says this is okay. So what's wrong with this? We even showed y'all this in class, guys. Y'all might not remember it. How do I turn this thing off? Yeah, no way we can stop this. We showed y'all that in class. But this is what we're talking about. So when you hit compile, it don't check to see, all it checks is syntax. It don't mean you didn't, the rung is going to work. It just means it's in the right format, right? Understand that? So I've heard that before. Well, I checked it with that thing up there, right? I checked it. Huh? Did y'all say that? Y'all didn't say that, did you? Y'all, I don't. If you did, but and this is what I wanted to make sure y'all understood that if I put a circuit into a PLC, I've got to be able to control it. I can't control the circuit anymore. That'd be awful out in the industry. You start a motor up, and then what? It don't work anymore, yeah. Or you can't turn it off. Now, luckily, they left something in here for us. Or I can literally come in here. So that's output 1. So I can do this. Yeah, but I got to do this guy up here too because okay. No, it's basically it's the software and it's called a force. Now, guys, that's a really neat feature. But what's the problem? Well, the problem is you've taken all the safety that's built into the system. You can kill people by forcing things. So you really, 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 really got to make sure that you know exactly what you're forcing when you force something. So it's not, let's see what this does, right? Let's see what this does. Then you have to delete it, and then you can enter it, and then it goes back to automatic. So you can force inputs and you can force outputs. Most of your new PLCs, you have to deliberately build what we call a force table. So you have to say exactly which ones you're gonna allow to force. PLC 500 lets you just force any input and force any output that's inside these data files. So up here, this shows you the status of the bit, right? You understand? Down here, this allows you to force the bits. Yeah. The one shows it's true. Well, not necessarily. The one shows you if the switch is closed or if the switch is open. No, well, one would mean the switch would be closed, but if I was using an examine if open, then a 0 is true. So an examine if closed, a 1 is true in that bit. Examine if open, a 0 is true in that bit. And that gets people confused. So this is probably one of the most confusing instruction right here that we teach is these examine if open and examine if closed. Yeah. And that's what this is one of the things that give people mistakes on a PLC. The problem is if I use an examine if closed, then I would have to use a normally open for a push button, for a stop button. Not normally open. We'd have to use an examine if closed instruction. You understand that, yes or no? So if I was going to draw this in PLCs, and this is a very important concept to understand, guys. So in motor controls, if I was going to draw this circuit right here, this is a standard start-stop station. We call this thing a start-stop station. We call it a memory. We call it a seal-in, and it's also called a 3-wire control. Is I would come over here, and normally what we do is over here we usually put a stop button right there. That's normally closed. And then I'll come over here and I'll put a start button right here, which is normally open. And then I'd put a seal in right here. And then I would come over here and then I'd put a symbol for my coil. And then if we call this M, then we would call this M. And we'd call maybe this stop. And we call this start. Now this is motor controls. Okay. So if I come over here, right here in PLCs, and I do this for that, and I do this, and then I do this for that, and then I come over here and do this for that, and then I come over here and put my output over here, oops, in PLCs, then we just screwed up. So this is an examine if open. This is an examine if closed. Then if I call this, this is the output energized. And of course, this would be the same thing for that one. Okay. Okay, so this is an examine if open. So it means this guy is true if it's open. And I come over here and I'm using a normally closed switch. Well, what's the problem? I'm using an examine if open instruction, and I'm using a normally closed switch. This says it's true if it's open. So what's going on? So what that means, to make this work, I would have to use a normally open contact, right? You understand? Everybody understand that? And then I use an examine if open instruction. It's open, so it's true, right? You understand that? So here I'm using a normally open push button for a stop button, because I'm using an examine if I'm saying if it's true, if it's open. Well, I want this to be true to start off with, right? I want this rung to be true. Okay. I'm using an examine if open instruction. So that means for my stop button, I would have to use a what? To get flow through that, I would have to use a normally open push button for a stop button. What's the problem with using a normally open push button for a stop button? What if the wire breaks going to the stop button? Well, that means I can't stop my motor anymore, because I would be getting an open all the time, and we cannot use a normally open contact for a stop button, right? You understand? Now, if it's not a stop button, I can use whatever I want to, but a stop button has got to be a normally closed push button, because if the wire breaks on the button on this input going to this PLC, it would see it true all the time, and I could not. I mean, it would see it true all the time, and I wouldn't do that. So that means in my PLC for a stop button, I got to use an examine if closed, because I'm using a switch that is normally closed, right? You understand? This makes sense now? So I have to use an examine if closed, because why? My push button is normally closed, and we say, okay, it's true if it's closed. And that's why we have to use examine if closed, or what in PLCs we call in motor controls we call a normally open contact. But in motor controls, excuse me, when I get this right, in PLCs it is not a normally open contact. It is a instruction that says examine if closed and examine if open, and that's talking about what I hook up to this guy right here, to these input ports. Not e-stop stops. Y'all understand the difference between an e-stop and a stop? An e-stop is supposed to kill power to every non-critical device, and it don't necessarily mean everything. So an e-stop button is different than a stop button. Every motor that I know of has got a stop button somewhere, not an e-stop. When you hit the e-stop, it's not only going to kill that motor, but it's going to kill everything in there, right? You understand? Power to almost everything. So you need, and the e-stop has to be a normally closed push button. It has to be, and a stop button is supposed to be, right, according to OSHA. But you get people, I've seen people teach this. This guy in this book teaches that. He'll use an examine if open for a stop button in this textbook right here. And you'll see it on videos all the time. And I did the same thing. Until I understood what's going on. And we'll demonstrate that. I'll hook up a motor to this guy. We got a motor up here. I'll pull out that stop button. I can hit it from now to doomsday, and that motor's going to keep running because I can't stop it. So that's something when you use that examine if open and examine if closed. If you want that thing, if you're going to use a normally closed push button, normally we use an examine if closed instruction, normally. Now for contacts inside your PLC, your program, that's the only time this comes into play, when you start dealing with push buttons, right? You understand? And you need to open something up when the push button, when a normally closed is pushed, and you're going to have to use an examine if closed instruction. And that's the only way I can teach it. I don't know. Motor controls, that's what we would use. PLCs, for that circuit right there, this is what we'd use right here. We'd use two examine if closed instructions there. By the way, some people will do it this way too. Don't get upset. It works just as well. Over in Germany, they like to do it this way. And you'll see a lot of people teach it like this. They'll come in and put their seal in first, and then they'll put their stop button right here in their diagram. Still works the same, right? As long as the stop is in series, it'll still break the circuit. So you'll see that done a lot too. And some people say it's because of the scan or something like that. It scans it stop first. Here it don't, I don't know, but to me it don't make any difference where you put it at. Motor controls, we usually put it on the left hand side, but it will work on the right hand side. So this is gonna mess you up in motor controls, right? And because automatically you see this as a normally open push button instead of a WAD instruction. Yeah. So if you want something to be true when the button is closed, that's the. So what we're talking about. So this instruction right here, it looks for a 0 in that input table. An input is true. This instruction right here looks for a 1 in the IO table. So you can't say a 1 is always true, can you? It depends on the application. It's just like, you know, the way we teach it in digital. I got full glasses of water and empty glasses of water up here. I could say the empty glasses of water is a 1 and not full glasses are 0s. All you got to do is have two combinations. In fact, RS-232 uses a minus voltage for a 1 and a plus voltage as a 0. So if you think always a 1 is going to be the most positive and a 0 is going to be the most negative, then you. What do you mean? That's the way the current is flowing. But of course, when we represent digital information, the most widely used, we got two methods that are widely used. One of them is to use a voltage to represent digital information, and the other one is to use a current. Now, what advantage does a current have over a voltage? Well, current's going to flow either way. If you have a voltage and you've got resistance, you're going to have a current. Usually when we use voltages, we use very low current. The problem with using voltages is electromagnetic interference can change voltage levels. So voltages are susceptible to EMI. Currents, it's real hard for an EMI to change current, right? You understand? So we have something called a 4 to 20 milliamp current loop. So this right here might represent a 0, and this right here might represent a 1. So you always got current flow. The biggest disadvantage, and this is widely used in industry, 4 to 20 amp current loop, because you have so much noise out there. This is widely used. But this guy wouldn't support it. This guy, and you can use it for analog too. So 4 could be the minimum value, 20 could be the maximum value, 4 could be a 0, 20 could be a 1, or you could have anything between that range. And you'll see this in industry, especially that's got a lot of, especially DC motors. They'll use 4 to 20 milliamp. So what would I need for this? Well, I could buy an IO module. I could slap it on the side, and it would do 4 to 20 milliamps, right? So that's the big thing about having these modular PLCs. Normally, by default, they support voltage. Common for analog is 0 to 10 volts using voltage. This is pretty standard. I think the Siemens that we have, you can set up the analog ports for the 314s we have. I think it's got two current loops and 3 analog. I think 3 voltage ports on their analog ports over there, if I think right. So there's a lot of things we can use besides voltage, and of course these are the two ways. We can't use resistance. Why? So normally we use either voltage or we use current to represent information going into the PLC, and this is also true for any computer. Okay, guys, what y'all can do is y'all can go ahead and take y'all a break, and then we'll meet back down at the lab.